Hello, my dear students. Welcome to the session continuation of important observations from our electronics concepts. In this session, with respect to module 2 rectifiers, that is AC to DC converters, I would like to discuss about concept of effect of source inductance on single phase rectifiers and dual converter concept. All of you concentrate. First, we have to start with effect of source inductance on single phase fully controlled rectifier or full wave rectifier is also called two pulse converter. Let's consider Ls is the source inductance. Friends, we know that without considering source inductance effect, this is the output voltage waveform and this is the output current waveform. The average output voltage is equal to 2 Vm by pi into cos alpha. If you don't consider the source inductance effect, these are the waveforms and this is the output voltage. Now the question is, if this source inductance effect is considered, what happening? By considering the source inductance effect, if you draw the waveforms, there is a overlapping of the thyristors. Due to source inductance, the thyristors are overlapped. When the thyristors are overlapped, during that angle, where mu is the overlap angle, during that angle, the output voltage falls to 0. That output voltage falls to 0. That means what is the observation here? Due to source inductance effect, in full wave rectifier, not only in full wave rectifier, in any rectifier, due to source inductance effect, the average output voltage is reducing. Not only reduction of average output voltage, the conduction angles are increasing, the overlapping of devices also takes place. In detail about this, these points I given, please go through this one. Due to source inductance, current through incoming and outgoing thyristor is not suddenly falling, not suddenly rising. This observation we are saying here. The current is slowly increasing, the current is slowly reducing, slowly rising, slowly falling. Because of that, there is an overlapping of the devices. In full wave rectifier, how many thyristors are overlapping? All 4 thyristors are overlapping. Very important observation, students. In a single phase full wave rectifier, due to source inductance effect, how many thyristors are overlapped? 4 thyristors are overlapped. That observation is also important. Because of source inductance, during some angle mu, that angle is called overlap angle. All the 4 thyristors are overlapped. Load is short circuited and output voltage falls to 0. Then what is the effect of source inductance? These are the different effects due to source inductance. One is all the 4 thyristors are overlapped due to source inductance effect in full wave rectifier or fully controlled rectifier. The average output voltage is reducing due to source inductance effect. Average voltage also reducing. The conduction angle of thyristors are increasing. We know that in a full wave rectifier, without source inductance effect, each SCR conduction angle is pi. If we consider the source inductance effect, each SCR conduction angle is pi plus mu square. This is the effect of source inductance. Conduction angles are increasing. Average output voltage is reducing. All the 4 thyristors are overlapping. Even source current waveform is also changing. If you draw the source current waveform, that source current waveform becomes trapezoidal. We know that in full wave rectifier, without source inductance effect, what is the source current waveform? It is a square wave. But if you consider the source inductance effect in full wave rectifier, that source current waveform becomes a trapezoidal waveform. That is, the source current waveform is also affected. Source current waveform is also affected. These are the effect of source inductance on single phase full wave rectifier. Now we have to calculate how much voltage is reduced due to source inductance effect. Before that, this point also you have to concentrate. Source current waveform becomes trapezoidal. It is closer to sinusoidal. Source current waveform is crossing 0 at omega t equal to alpha plus mu by 2. This one. This is the crossing point. The source current waveform is crossing at omega t equal to alpha plus mu by 2. Then from this, with the source inductance, what is the displacement factor? Based on this formula, already question is there in GATE exam. Very important, students. Without giving overlap angle, if displacement factor is asked in full wave rectifier, answer is cos alpha. With the overlap angle, by giving overlap angle, if the displacement factor is asked, then what is the displacement factor? Cos of alpha plus mu by 2. Very, very important observation that you have to concentrate. Without Ls, what is the displacement factor? Cos alpha. With Ls, displacement factor is cos of alpha plus mu by 2. That is the observation. Then The source current waveform during alpha to alpha plus mu, the current is changing from minus I naught to plus I naught. With that observation, I'm not giving detailed derivation here, that I given the steps, please go through this one. But during your preparation, no need to concentrate on these steps, because a quick revision, directly go through the formula, students, very important. Already based on the effect of source inductance on single phase full wave rectifier, questions are framed in GATE exam. To solve the questions with respect to this concept, direct formulas are important. Directly they are asking the questions from formula, students. Then what is the average load current formula? This formula is for only for full wave rectifier. The average load current, this formula you have to concentrate. I naught equal to Vm by 2 omega Ls into cos alpha minus cos of alpha plus mu. This is the average load current formula. This is the first formula you have to remember. Next. Then what is the average output voltage, friends? With source inductance. With source inductance, the average output formula. The average output voltage formula. Vm by pi into cos of alpha plus mu. This is one way to calculate the V naught with source inductance. And one more formula with source inductance. This is the third one, friends. Whatever the numbering I given now, that numberings you have to remember. Very, very important. 2 Vm by pi into cos alpha minus 2 omega Ls by pi into I naught. That equal to Vm by pi into cos alpha minus 4f Ls into I naught. That is due to source inductance effect. This much of voltage is reducing, friends. Due to source inductance effect, this much of voltage is reducing. We know that without source inductance, this is the voltage 2 Vm by pi cos alpha. But with source inductance, this much of voltage we are subtracting now. We are subtracting means this voltage is reducing. Therefore, from 2 and 3 indicates average output voltage with Ls. This 2 indicate the average output voltage with Ls. 3 is also indicate the average output voltage with Ls. This I written this formula with respect to mu. This I written in terms of Ls. Very important. Both are average output voltages. This is in terms of Ls, students. Source inductance I written. This is in terms of mu I written. By giving the mu, if it is asked what is the average output voltage, use this formula. By giving only source inductance, if it is asked what is the average output voltage, use this formula. These two formulas important. First formula important, second formula important, third formula is also important, students. Then what is the voltage reduction due to source inductance? How much voltage is reduced due to source inductance? This is delta V naught. I told already, in full wave rectifier, not only in full wave rectifier, every rectifier, because of source inductance, the average voltage is reduced. Now the question is, in single phase full wave rectifier or fully controlled rectifier or two pulse converter, due to source inductance effect, how much voltage is reduced? 4f Ls I naught, 5-star gunshot formula. Due to source inductance effect, the average output voltage is reduced by 4f Ls into I naught. That you have to concentrate. Next, this is the reduction of average output voltage due to source inductance effect. This delta V naught is also written like this. Delta V naught is also written like this. This formulas also you have to remember. This is the 3 and this is the 4, students. This is the relation 4. And you have to remember this is the relation 4. Then this is the relation 5. This delta V naught also I am writing in two formulas. This is in terms of inductance. This is in terms of mu. This use this formula or use this formula, you can get same answer. But if they given Ls values, use this formula to calculate how much voltage is reduced. If they given mu value, use this formula to calculate how much voltage is reduced. That means with the source inductance effect, there is a change of voltage from without source inductance and with source inductance. That change of voltage is defined as a voltage regulation switch. Okay, this is the summary. Average output voltage with Ls. Average output voltage without Ls, 2 Vm by pi cos alpha. With Ls, this is the average load current. This is with source inductance. Ls is source inductance. This is the average output voltage formulas. Two formulas for average output voltage. This is the reduction of average output voltage. For reduction of average output voltage also two formulas, friends, that you have to concentrate. Then what is the voltage regulation due to source inductance? There is change of voltage now. Without Ls 2 Vm by pi cos alpha. With Ls this is the voltage. There is a change of voltage now. There is change of voltage means that is called voltage regulation. Then what is the voltage regulation due to source inductance? This is very, very important 5-star gunshot formula. 4 pi f Ls into I naught by 2 Vm cos alpha. This is one way to write the regulation formula. And this is also regulation formula. This is also regulation formula, voltage regulation. See, every formula I am giving two formulas. For every formula I am giving two representations. Now, one is in terms of source inductance, another is in terms of overlap angle. That you have to concentrate. If this formula is applied for the diode rectifier, for diode rectifier, what is the firing angle, students? Firing angle is 0 now. Substitute firing angle 0 here. Cos 0, 1. 1 minus cos mu by 2. That is, what is the voltage regulation in diode rectifier? 1 minus cos mu by 2. That is a full wave diode rectifier. And one more observation here. We know that if the current is increases, average output voltage is reducing now in this formula. If the current is increases, the average output voltage is reducing. That is the observation, friends. Then even frequency increases, average output voltage is reducing now. This is in terms of frequency. The frequency increases, average output voltage is reducing. Next, even source inductance is increases, average, if source inductance is increases, average voltage is reducing. Even overlap angle is increases, average voltage is reducing. These are the effects. Current is increased, voltage is due to source inductance effect. Frequency increases, average voltage reduces. Inductance increases, average voltage reduces. Mu increases, average voltage reduces. From this, what is observation? Frequency increases, average voltage reduces. Mu increases, average voltage is reduces. Right hand sides are equal. Then we can equate left hand side. Then what is this observation? If the frequency is increases, overlap angle is increases. That is, with the source inductance case, if you try to operate the circuit at high frequency, there is a more overlap angle. In with LS, at high frequency, the overlap angle is more. In single phase full wave rectifier, due to LS, all 4 SCRs are overlapped. That you seen. How many thyristors are overlapped? 4 thyristors are overlapped, friends. Every formula is important. You have to remember I0 formula, V0 formula, voltage regulation formulas you have to remember, friends. Voltage regulation and delta V0 formula also you have to remember. Then this is the equivalent circuit with source inductance. This what this circuit indicates. This circuit indicates effect of source inductance on full wave rectifier. If you apply KVL in this loop, friends, if you apply KVL in this loop, then we can get this is the formula. This is the equivalent circuit of the effect of source inductance that you have to concentrate. At what slope the average output voltage is reducing? This is the reduction of average output voltage now. The reduction of average output voltage means it is having positive slope or negative slope? Negative slope. At what slope it is reducing? 4f ls. It is reduced by a slope of 4f into ls. 4f into ls or 2 omega ls by pi. That is the slope of reduction of average output voltage. That points also you have to concentrate. This is one question that you have to practice. Simple theory question. Average voltage reduction in the phase controlled AC to DC converter is due to both source inductance and load inductance. Important. I already explained, due to load inductance also average output voltage is reduced. Source inductance also average output voltage reduced, friends. But point to remember, for example, if you take the source inductance and load inductance, friends, source inductance and load inductance case, load inductance. If we consider the source inductance and load inductance, due to source inductance, average voltage is reduced. Here also average voltage is reduced. Due to load inductance also average voltage is reduced. The conduction angles are increases. Load inductance also conduction angle is increases. Then due to source inductance, overlapping of thyristors are exist. Overlapping of thyristors. But due to load inductance, there is no overlap. This is the main difference. There is no overlap, students. Due to load inductance, the devices will not be overlap. Due to source inductance only, the devices are overlap. There is no overlap. This observation is important. That means which inductance causes the overlapping of the devices? Only source inductance causes the overlapping of devices. But load inductance does not cause the overlapping of the devices. This is already given. Average output voltage, conduction angles, overlapping of the device. Source inductance causes the overlapping, but load inductance does not causes the overlapping. Next, what is the effect of source inductance on single phase half wave rectifier? In single phase half wave rectifier also the average output voltage is reduced. Then without source inductance, this is the average output voltage, friends. with source inductance with Ls. This is the current expression in half wave rectifier. Still now no question in half wave rectifier, but in future we can expect. For your exam point of view also it is important. This is without Ls case. This is the V naught. With Ls case, this is the I naught formula and this is the V naught formula. With Ls case, this I written in terms of overlap angle. I written this average output voltage formula in terms of inductance also. Inductance also. That means in half wave rectifier due to source inductance effect, how much average voltage is reducing? FLSI naught. In full wave rectifier, 4 FLSI naught is reducing. But in half wave rectifier, how much is reducing? FLSI naught is reducing. That is, in single phase half wave rectifier due to Ls, the average output voltage is reduced by FLSI naught or omega Ls by 2 pi into I naught. Omega is 2 pi F naught. If you simplify this, we can get this one. That you have to remember. Then what is the voltage reduction due to Ls? That is FLSI naught. What is the voltage regulation due to Ls? This is the voltage regulation due to Ls. How to calculate FLS into I naught by Vm by 2 pi into 1 plus cos alpha. Yeah, this is the voltage regulation due to Ls in the case of half wave rectifier. This formula for half wave rectifier. Then if the question is asked, this is the previous gate question that you have to concentrate. Let's consider single phase half wave diode rectifier given like this. Without Ls, what the each diode conduction angle? This is pi, this is pi. That is without Ls, each diode conduction angle is pi pi. But with source inductance, I told already, due to source inductance effect, the overlap angle is added. Then conduction angles are increases now. Conduction angle is increases. How much angle it is increases? It is increased by mu angle, where mu is the overlap angle, students. That means D1 conduction angle is greater than 180. Even D2 conduction angle also greater than 180. Without Ls, each is 180. With Ls, greater than 180. Why? Because of overlapping of the devices. That you have to concentrate. Then this problem you have to practice with respect to single phase half wave diode rectifier and average output voltage conduction angle. This statement I already given. This statement I already given. But you please go through this one. This observation is important. Next. And this problem also you have to practice. Then what is each diode conduction angle? Pi plus mu. Actually, without source inductance pi, with source inductance this is the pi plus mu. What the average output current? This formula already you know. Then you have same formula whatever I derived, but alpha equal to 0 here. It is a diode rectifier now, alpha equal to 0. This is the full wave rectifier, friends. Full wave thyristor rectifier I derived the formula, but in diode rectifier substitute alpha equal to 0. And then this overlap angle is 44.19. Then what is the diode conduction angle? 180 plus mu. No? Each diode conduction angle is 180 plus mu. Extra mu is added because of the source inductance effect. Then how much? 224.19 degrees. Very, very important model. Please practice this model. That you have to concentrate. Then this problem I already solved. D1 conducts for greater than 180 degrees. D2 also conducts for greater than 180 degrees because of the source inductance effect. Because of the source inductance effect. And this problem also you have to practice. Okay, this also very important model, students. That you have. This is also due to source inductance concept. This is also due to source inductance. Direct formula you can expect. Direct problem you can expect, students. This problem you have to practice. Next. Then average output voltage, both source inductance, load inductance, average output voltage is reduced. Then this problem also you have to practice. Very, very important that you have to practice. This also due to source inductance concept. This is based on the source inductance concept. Here you are finding the overlap angle. 3.17 degrees we got. Please practice the questions. Please practice the questions. And this is also based on the source inductance concept. Here it is asking that what is the overlap angle? The overlap angle mu equal to 4.8 degrees we are getting in this problem. 4.8 degrees. These are the different models of questions with respect to source inductance concept. Then what is the effect of source inductance on full wave rectifier that I explained? What is the effect of source inductance on half wave rectifier also that I explained? And one more important concept with respect to single phase rectifiers, that is a single phase dual converter. A dual converter is a how many quadrant converter? That you have to concentrate. A dual converter is the anti-parallel connection of two full wave rectifiers. Why do go for the dual converter? To control the motor in 4 quadrants. The statements I given, please go through this one. But very important is this observations. A single phase dual converter is the anti-parallel connection of two full wave rectifiers. It is anti-parallel connection of two full wave rectifiers. The purpose of using the dual converter is without reversing the armature terminals or field terminals of a motor. To control the motor in 4 quadrants, not in 2 quadrants, 4 quadrants, we are using the dual converter switch. That is, it is anti-parallel connection of two single phase full wave rectifiers. If it is a single phase dual converter, two single phase full wave rectifiers. If it is a 3-phase dual converter, two 3-phase full wave rectifiers. That is the only difference. It is a 4-quadrant converter switch. Dual converter is a 4-quadrant converter. For a single phase dual converter, number of thyristors equal to 8. For 3-phase dual converter, number of thyristors equal to 12 switches. We know that it is operated in non-circulating current mode and circulating current mode. A dual converter is operated in non-circulating current mode and circulating current mode. Then it is a 4-quadrant converter. In first quadrant, it is a forward motoring mode. Forward motoring mode. In second quadrant, it is a forward braking mode. First quadrant, V0 greater than 0, I0 greater than 0. This is also asking in exam. In second quadrant, V0 greater than 0, I0 less than 0 swings. In third quadrant, V0 less than 0, I0 less than 0. In fourth quadrant, V0 less than 0, I0 greater than 0 swings. V0 greater than 0, I0 greater than 0, power is positive. Power is delivered from source to load. V0 greater than 1 is positive, another is negative, power is negative. Then power is delivered from load to source. Power is negative means load to source. That point you remember. Here power is both are negative means power is positive. Power is delivered from source to load. One is positive, another is negative, power is negative. That you have to concentrate. Next, circulating current mode of operation. Circulating current mode means both the converters are operated at a time. Then only circulating currents are exist from one converter to another converter. When the circulating currents are exist, both the converters are operating. This converter is on state, this converter is on state. Then only circulating currents are exist. Circulating currents means the currents flowing from one converter to another converter. Generally, there is a load current. Along with load current, there is a currents from one converter to another converter. That currents are called circulating currents. Sir, why circulating currents are exist, sir? Because of voltage difference between the two converters. When the voltage difference is exist, if two converters are on state, this is on state, this is also on state, then only the circulating current mode of operation is existent. To reduce the circulating currents, we are using center tap reactors. That is, in circulating current mode only center tap reactors are required to reduce the circulating currents. What do you mean by non-circulating current mode? To eliminate the circulating currents, if one converter is on state, another converter is off state. That is called non-circulating current mode. But point to remember, in circulating current mode, alpha 1 plus alpha 2 equal to 180 degrees. This condition is very important. Already in different competitive exam, this condition is framed. That is, we are controlling the firing angle in such a way that alpha 1 plus alpha 2 equal to 180 degrees. In which mode? Circulating current mode of operation. This is very, very important. How to select the firing angles in a circulating current mode? This condition is applicable only for circulating current mode. This condition is not applicable for non-circulating current modes. Yes. And these are the circulating current mode of operation waveforms. This is a V01 waveform. This is a V02 waveform. And then this is the average output voltage. This is the output voltage waveform. This is the voltage across the reactor waveform. No need to practice the waveforms that you have to concentrate. Then in circulating current mode of operation, there exists a circulating currents now. What is the expression for circulating current? This is the expression for circulating current. What is the peak value of circulating current? The peak value of circulating, this is the summary point. In circulating current mode, these points are very, very important that you have to concentrate. Circulating current mode. Alpha 1 plus alpha 2, 180 degrees. V0 is 2 Vm by pi into cos alpha 1. The reactance voltage is 2 Vm sin omega t. This is the circulating current expression. Peak value of circulating current equal 2 Vm by omega Lr into 1 minus cos alpha 1. Next, what do you mean by non-circulating current mode? In non-circulating current mode, at a time only one converter is operated. No need of any center tap reactors. Why? There is no circulating currents means no need of any center tap reactors in the case of non-circulating current mode of operation. Then what is the quadrant operation of dual converter? This is very important. No need to make in detail explanation here. Directly you have to remember this quadrant operation. In quadrant operation using non-circulating mode, quadrant operation using circulating current mode, students. We may expect a question like this. In non-circulating current mode, for motoring mode, which converter is operated? Converter 1, firing angle less than 90. In forward braking mode, converter 2, firing angle greater than 90. In reverse motoring mode, RM in the sense reverse motoring mode. RM in the sense reverse motoring mode. This I given, please go through this. Converter 2 operated, firing angle less than 90. In reverse braking mode, converter 1 is operated, firing angle greater than 90. They will ask the which converter is operated, what the firing angle is. In the case of non-circulating. In circulating current mode, just modify this one. Just remember this one. Here alpha 1 less than 90 na, alpha 2 greater than 90. Both converter 1 and converter 2 is operating. Converter 1 is on state, converter 2 because it is circulating current. Yeah, this is the quadrant operation of non-circulating current mode. This is the quadrant operation of circulating current mode. But what type of question we can expect from this one? In which, that is, in first quadrant, which converters are operating? What are the firing angles? We may expect which converter is operating, what are the firing angles, students? That models of questions. To solve that models of questions, this observation is important for circulating current mode. Just remember this one extra. Here alpha 1 less than 90 na, alpha 2 greater than 90. Alpha 2 greater than 90 na, alpha 1 less than 90. Here only one converter na, but here two converters. That is only difference, students. That you have to concentrate. This is the quadrant operation of the circulating current mode and non-circulating current. These are the differences between non-circulating current mode and circulating current mode of operations. At a time only one converter is operated, but here at a time both the converters are operated. No need of center tap reactors, but here center tap reactors are required. Yes, non-circulating current mode is slow response, but it is a fast response. This is the main advantage of circulating current mode. This is a fast response. In non-circulating current mode, because there is no circulating currents now, rating of thyristors are less. Rating of thyristor is high because of circulating currents. Once there is no reactor, less size, but large size because reactors are required. There is no reactors, rating of thyristors are so less now. That's why it is a less cost, but it is a costly. Here there is no circulating currents, power losses are less, high efficiency, but it is a less efficiency because of circulating current. In non-circulating mode, there is a possibility of discontinuous mode, but there is a possibility of always in circulating current mode, there is a continuous mode. Then you have to answer these questions. Here it is asking that second quadrant. In second quadrant, which converter is operated? Converted to alpha 2 greater than 90 degrees. In which mode? Non-circulating current mode. This type of questions we can expect based on the quadrant operation. In circulating current mode, alpha 1 plus alpha 2 equal to 180 degrees. And you have to solve the peak value of circulating current. Important. And peak current through the thyristor 1. I circulating, peak value of circulating current plus maximum value of load current. Maximum value of load current is Vm by R. For the peak current through the converter 1, peak current through the converter 1 is 16.388 amperes. Peak current through the converter 2 is 5.548 amperes. That is, here only converter 1 firing angle is controlled now. That's why converter 1 is carrying the high currents. Like that you have to remember. For the converter for which firing angle is given, for that converter we have to add the load current also, because that converter is supplying the load current. And converter 2 is carrying only circulating current. Converter 2 is carrying, for example, if alpha 2 given, if alpha 2 is given, then peak current plus load current, peak current plus load current. But here alpha 1 is given, peak current plus peak circulating current plus load current for that converter 1. Converter 1. Simple, students. Alpha 1 is given, load current, maximum load current you have to add to the converter 1. If alpha 2 is given, load current you have to add to the converter 2. Because that alpha indicates that converter is controlling. If that converter is controlling means that converter is supplying the current to the load. That is the meaning. This model of question is very important. This is about the dual converter concept. Friends, with this, with respect to module 2, rectifiers, that is AC to DC converters, the concept of effect of source inductance on rectifiers and dual converter concept is completed. This is about the session. Thank you.